Hello, and welcome to The Explainer. Today, we're grabbing a word you see and hear every single day, pure, and we're going to blow the lid off what it really means in the world of science.
I mean, think about it. You're walking down the grocery aisle and you see it everywhere. Pure milk, pure juice, pure salt. It's on everything. But what if I told you that, from a scientific point of view, almost none of that stuff is actually pure?
And here's the twist. See, for most of us, when we say pure, we just mean that nothing yucky has been added to it, right? It's not adulterated. But for a scientist, pure has a way stricter definition. It means a substance is made up of only one single type of particle. That's it. So yeah, that carton of milk, to a chemist, it's this incredibly complex soup of water, fats, proteins, and a bunch of other things. It's the total opposite of pure. And you know what? Most of the matter we deal with every day is just like that. It exists as a mixture of different things. So if our world is basically built on mixtures, we probably ought to figure out what they are. This is really the first big step to understanding what scientists even mean when they talk about purity.
Okay, so a mixture is what you get when you combine two or more pure substances, but, and this is the critical part, there's no chemical reaction. They're just hanging out together. And because of that, you can actually separate them again using physical methods, like boiling salt water to get the salt back.
Now, mixtures kind of come in two main flavors. First, you've got your homogeneous mixtures. These are the ones that look the same all the way through, like salt dissolved in water. You can't see the individual parts. And then you have heterogeneous mixtures. These are, well, they're chunky. You can totally see the different components, like oil floating on top of water or a mix of sand and iron bits. All right, let's zoom in a little bit because even within those big categories, we can break mixtures down into three more specific types that, trust me, you run into all the time. First up, we've got the solution. This is your classic homogeneous mixture. The particles that are dissolved in it are so incredibly tiny, we're talking less than a nanometer, that they never settle out and they don't even scatter a beam of light. Think about sugar that's completely vanished into your tea. That's a solution. Now, on the complete opposite end of the spectrum, you have a suspension. This is a heterogeneous mixture where the particles are big enough for you to actually see them. They're totally unstable, so if you just let it set, all the bits will eventually sink to the bottom. Muddy water is the perfect example here. And right in between those two, you have this really fascinating character, the colloid. Its particles are bigger than in a solution, but smaller than in a suspension. And this is why a colloid, like our old friend milk, can totally trick you. It looks smooth and uniform, but it's actually heterogeneous if you could zoom in far enough. So what's the dead giveaway for a colloid? Well, it has this one cool trick up its sleeve. Because its particles are just the right size, they scatter a beam of light and make the beam's path visible. This awesome phenomenon is called the Tyndall effect, and it's the secret test to tell a colloid from a true solution. And you've definitely seen this in real life. You know when you see those beautiful, sharp beams of sunlight cutting through the mist in a forest? That's it. You're literally watching the Tyndall effect. The tiny little water droplets in the air are acting like colloidal particles and scattering the sunlight. Okay, let's do a quick side-by-side. Solutions are clear and super stable. Suspensions are cloudy, unstable, and the chunky bits will always settle out. And colloids are that tricky one in the middle. They look stable like solutions, but they give themselves away by scattering light. Okay, so we spent a lot of time on mixtures. Now it's time to swing back to our original question and get to the bottom of what scientists actually call pure. So it turns out it's actually a pretty exclusive club. In science, there are only two categories of pure substances: elements and compounds. That's the entire list. So what's the deal with these two? What's the real difference between an element and a compound? Well, it all boils down to a really fundamental chemical difference. An element, like pure iron or pure oxygen, is like the ultimate building block. It's a basic form of matter you just can't break down any further using chemical reactions. A compound is what you get when you take two or more of those elements and chemically snap them together to form a brand new substance, like H2O, water. And this is the million-dollar question. What really separates just stirring some iron and sulfur powder in a bowl from actually heating them up and forcing them to create a new compound? Let's check out a quick experiment that shows this perfectly. So, picture this.
First, we just mix iron filings and sulfur powder together. It's just a simple mixture, right? And watch this. A magnet can swoop in and pull the iron right back out. But then we take that exact same mixture and we heat it up a lot. A chemical reaction kicks off, and suddenly we have a totally new substance, iron sulfide. Now try that magnet again. Nothing. It has zero effect. The iron isn't really iron anymore. It's locked into a completely new compound with totally new properties.
So what's the final showdown look like? A mixture is just a physical jumble where all the parts keep their own identities and can be separated pretty easily. But a compound, that's a brand new substance forged in a chemical reaction with its own unique properties and a fixed recipe. You can't get the original stuff back without another chemical reaction.
And that's really the bottom line here. A physical change, like mixing, is just rearranging the furniture. But a chemical change? That's like tearing down the whole house and using the pieces to build something completely new. That's the fundamental difference between a mixture and a pure compound. So now you're in on the secret. You know the scientist's definition of pure. So take a look around you right now. The air you're breathing, the water you're drinking, the device you're watching this on, they're all mixtures. The question is, how does knowing this change the way you see the stuff that makes up your world?